Assalamualaikum and hello IB to all. Today we are going to present about second order differential equation for course Sscp 2613. Now I want to introduce my group member. This is me, Siti Maryam. We have Siti Aisyah, Rabiatul Adawiyah and Christina. So for introduction, the oscillation of the coilover on a bumpy road can be expressed by second-order ordinary differential equation (ODE). The retarding force due to the damper must be included in the ODE. You can assume that the spring length is equal to the equilibrium length of the spring in the unperturbed condition. This means that the weight of the automobile is ignored through this assumption. Next, we move to the question that given. First, we need to derive of solution to the second order ordinary differential equation of the coilover. Second, using suitable values for the constant in the solution, simulate displacement versus time graph for the undamped, underdamped, overdamped and critically damped condition. The last one, discuss the result obtained in the part 2. So for possibilities, we have 4 possibilities for this derivation. First, no damping, underdamping, critical damping, and overdamping. We move to no damping. This is a general equation using in no damping. Next, for example, we move to the equation given. As you can see from this equation, we have mass of 1 kg attached. The coil spring fixed to the coilover on one end. When force of 6 Newton applied, the spring stretched 1.5 meter from natural length. So, we need to determine position of mass as function of time after release if mass initially released from rest 1 meter to the right of equilibrium position. This is the solution for the question given. First, we need to refer to Hooke's law, which is F equal to Kx. The value of K is 4. We got the xt equal to cos 2t, and we need to include it to the xt and x prime t. So now, this is the graph of displacement versus time. The damping coefficient is 0, which is no damping, and the graph given is sinusoidal.
Next is underdamping. Underdamping consists of complex roots. We will see the example of this underdamping equation. Underdamping is the condition in which damping of an oscillator causes it to return to equilibrium with the amplitude gradually decreasing to 0. System returns to equilibrium faster but overshoots and causes the equilibrium position one or more times. This is the example for underdamping. Example 2, which is underdamped motion. X squared plus x plus 4x equal to 0. Roots equal to r equal to negative 1 plus minus z 1 minus 16 over 2 equal to negative 1 over 2 plus minus I z 15 over 2. Negative 1 over 2 which is alpha and z 15 over 2 which is beta. So final answer is xt equal to e the power of negative 1 over 2 c1 cos 15 over 2t plus c2 sin 15 over 2t. This causes oscillation. This is the graph for the damping coefficient equal to 1, which is underdamping.
The next motion from second order of differential equation is overdamping. So what is overdamping? From the definition, we can see that overdamping is the condition in which damping of an oscillator causes it to return to equilibrium without oscillating. The oscillator will move more slowly toward equilibrium than in the critically damped system. So, overdamping is another way to classify the motion of the spring, and as you can see, this is the formula that we have to use to find the roots, which is R1 equal to negative C plus square C to the power of square minus 4 mk over 2m. From this, we can also have to make sure overdamping has a real and distinct roots. So, let us see the example from the question and we will solve it down. For this overdamping spring, the equation below brings us to overdamping situation, which is x squared plus 5x plus 4 equal to 0. Here, the characteristic equation is r, which is r squared plus 5r plus 4 equal to 0. From this factor, we can write r plus 1 times r plus 4 equal to 0. Then, we will get the roots, which is r equal to negative 1 and negative 4. With this information, we can immediately write down the form of solution, which is xt equal to c1 e to the power of negative t plus c2 e to the power of negative 4t. When we look at this form and decide what will happen to the spring over time, if t goes to infinity, both of these exponential expression will go to 0. So, we know that the position is going to go to 0 as time goes to infinity. So, we will expect the spring to return to its equilibrium state. So, no oscillation. And then once again, depending on the values for C1 and C2, it's possible to be 0 exactly once. Now, I will show you the graph that shows the position of the spring over time, which is the damping coefficient equal to 5.
The definition of critical damping is, it occurs when a system returns to its equilibrium position as quickly as possible without oscillating. This happens when the damping force is precisely enough to prevent any bouncing back and forth, ensuring a smooth and swift stabilization. For root characteristic of critical damping, it is real repeated root, which is R equal to negative C over twice amount of mass. From the characteristic equation, we can write down as R squared plus 4R plus 4 is equal to 0. And this is a factor of R plus 2 to the power of 2 is equal to 0. And from this, we can say that the root is R is equal to negative 2, which is repeated. X of t is equal to C1e to the power of negative 2. And since it is repeated, then plus C2 te to the power of negative 2. Factoring the equation to e to the power of negative 2, C1 plus C2t. So, as t goes to infinity, the exponential is going to be 0. Since there is no cos or sine in this equation, there is no oscillation occur in this case. The equation of C1 and C2 will be 0 if t is equal to negative C1 over C2. It may be 0 exactly once, and it is called overshoot. This is how critical damping looks like on position versus time graph.